I'm very happy to introduce Federico Holik from University of La Plata. His presentation will be about on the interpretation of states as non-commutative measures in generalized probabilistic models.
The story that I'm going to tell you starts in the year 1900 during the International Congress of Mathematicians held in Paris. David Hilbert presented a list of 23 problems of mathematics, which is, in his opinion, should occupy the efforts of mathematicians in the century to come. There are two remarkable things about this problem. The sixth problem. It is devoted to physics. That's something remarkable. And the second remarkable thing is that probability theory is included in the physical problem. So let me quote Hilbert. The investigations on the foundations of geometry suggest the problem. To treat in the same manner, by means of axioms, those physical sciences in which mathematics plays an important part. In the first rank are the theory of probabilities and mechanics. As to the axioms of the theory of probabilities, it seems to me desirable that the logical investigation should be accompanied by a rigorous and satisfactory development of the methods of mean values in mathematical physics and in particular in the kinetic theory of cases. So rigorous, satisfactory, and mean values. This is important words. So Hilbert himself dedicated big efforts to solve his sixth problem. His contributions were influenced in the development of relativity theory, but he also contributed to the development of quantum mechanics. Quantum mechanics acquired its rigorous formulation after a series of papers by Hilbert, von Neumann, Nordhend, and Wigner. It can be said that its definitive form was accomplished in the book of von Neumann. But the solution, one of the most important solutions to Hilbert's sixth problem came from, surprisingly enough, from measure theory. During the 30s, Kolmogorov presented his theory of probability, and if you look at these axioms, the first remarkable thing is that they are phrased in a measure theoretical framework. This allows to build a solid ground for computing probabilities and mean values, because it's a solid mathematical theory, well developed. The second remarkable thing is that these axioms include a lot of models in them. You can describe models in physics, in social sciences. There are many different theories that are synthesized in this set of simple axioms. But these axioms describe essentially functions on a measurable set, right? The essential mathematical object here is the notion of function. And an important thing is that states of classical statistical theories can be considered as Kolmogorovian measures. Observables are random variables, and random variables are measurable functions. Notice that the axiomatic formulation of classical information theory, in the sense of Shannon, depends, from a logical point of view, on the notions of probability and random variable. You open the Cooper-Thomas book or any rigorous axiomatization of information theory, and the first thing that you define is probability and random variable. But these probabilities can be rigorously defined using Kolmogorov's axioms. This will be important later. But at the same time, during the 20s and during the 30s, another problem with probability and other axiomatizations of physical theories was going on. The advent of quantum mechanics showed a model of probabilities which had many peculiar features. Let us quote Feynman. He says in this paper here, I should say that in spite of the implication of the title of this talk, the concept of probability is not altered in quantum mechanics. When I say the probability of a certain outcome of an experiment is P, I mean the conventional thing. That is, if the experiment is repeated many times, one expects that the fraction of those which give the outcome is questioned is roughly P. So there's no change. You make the statistics, and this is not changes. What changes, and changed radically, is the method for computing probabilities. Let us try to understand what he means. The first remark that I made is that in quantum mechanics, states are the mathematical object is no more a function. It's a matrix, or more generally, a density operator acting on a Hilbert space. This is a very different mathematical object. So, is it possible to cast this object here, a point in the convex set of quantum states, as a set of axioms? Yes, this is possible. One can define a measure in the lattice of projection operators on a Hilbert space. One puts these axioms, and using Gleason's theorem, for dimension greater than 3, it is possible to show that each measure of this kind is represented by a density operator. If you look at these axioms, and then you look at Kolmogorov axioms, you can see that there is a great similarity. But now, what have changed, and changed radically, is that here, instead of having a Boolean algebra, you have a non-Boolean algebra here. So the negation is a different logical operation, and the conjunction and disjunction from the operational point of view are different. In this way, if you want to compute the negation of an event, you know how to compute the probability. By this rule, you compute new probabilities out from old ones. And this is the same. If you know the probability of this, you know the probabilities of this, and vice versa. So it's telling you the rules, but the rules have changed, and changed radically. Because now the objects that represent this from a mathematical point of view are density operators. And this is, I will talk about this later, but this is in connection with the fact that in quantum mechanics we have contexts. The complementarity principle, described by Port for the first time, maybe, is that if you want to wholly describe a quantum system, you must perform different non-compatible experiments. So the quantum state defines, for each context, a classical Kolmogorovian measure. But the whole thing is a pasting of Kolmogorovian measures, but the whole thing is not a Kolmogorovian measure. It obeys a different set of actions, which are these ones. This is not the Boolean algebra. But the story didn't end here. In a series of papers, Murray and von Neumann searched for algebras more general than the bounded operators acting on a Hilbert space. And indeed, they found them. These new algebras are known today as von Neumann algebras, and their elementary components can be classified as type 1, type 2, and type 3 factors. It can be shown that the projective elements of a factor form an orthomodular lattice. Classical models can be described as commutative algebras. So the classical Kolmogorovian approach is included here as a particular case. The models of standard quantum mechanics can be described by using type 1 factors, 1m for finite-dimensional Hilbert spaces and 1 infinity for infinite-dimensional models. These algebras are isomorphic to the set of bounded operators on a Hilbert space. But this is not just a mathematical curiosity, because further work on the axiomatization of quantum field theory and systems with infinitely many degrees of freedom showed that more general factors at type 1 should be used. For example, in quantum field theory, type 3 factors appear in a natural way. But this is related to the peculiarities of these theories, because now, let us go back for a minute here. No, okay. So the fact is that the change in the algebraic setting makes radical changes in the properties of the states that you can define of the theories. States of quantum field theory are different and have different mathematical properties than states of standard quantum mechanics. And this is not an abstract mathematical physics problem. It's related to the problem in the end. Sorry. Que atención, por favor. It's related to very important problems in physics, because we have a right axiomatization of classical mechanics using symplectic manifolds. We have a right axiomatization of general relativity using Riemannian manifolds, pseudo-Riemannian. And we have a right axiomatization of standard quantum mechanics. We have the work of von Neumann. But in quantum field theory, we have divergences. We have a measure theory which does not work properly. Of course, we know how to fix it. But the problem gets even worse when we want to go into quantum gravity. So it is a need for physics to have sharp, rigorous, well-defined measure theoretic approach for computing probabilities. And this is very important, because if I want to speak about foundations in quantum field theory, I need a framework which allows me to speak about Kochen-Specker theorem, Gleason theorem. I want to speak about that. And to speak about that, I need a sharp theory. And we don't have this now. It's an open problem in nowadays physics. It's very important. So, in general, I will skip this, but one defines a state in a general von Neumann algebra as a continuous positive linear function, which is normalized. But then one can think about a generalized approach to probabilistic theories. Why? Because one can give an abstract formulation of what is a probabilistic state in a probabilistic model. If in these actions I put here a Boolean algebra, I regain Kolmogorov's approach. If I put the type 1 factor of standard quantum mechanics, I regain standard quantum mechanics. If I put a more general algebra, I can have quantum field theory or other theories with continuous degrees of freedom. But one could say more. One could think about more general theories. In this book, you can find examples of non-commutative models applied to the study of problems in finance, cognitive sciences, computer sciences, and so on. People is talking about this and trying to apply it. So, is it possible to give a unified approach, as in Kolmogorov's case, to generalized probabilistic models? What about interpretation? This is the problem of my talk. So we start from this, saying, well, there are states of physical theories which are not isomorphic to Kolmogorovian measures. They are something more complicated. So what can we say about the interpretation? This plurality has direct implications for information theory. As I told you before, standard books on classical probability theory rely on classical probability theory, or classical information theory, sorry. But if you change the states, you change the notion of random variable, you change the notion of state, well, then you have to do something else. So here we discuss how it changes. So, let us go to interpretation. Let me talk about our approach. One possibility is subjective probability. In this approach of Cox is a rational agent, deals with the Boolean algebra of assertion representing physical events. A plausibility calculus can be derived in such a way that the plausibility function yields a theory which is formally equivalent to that of Kolmogorov. But what we did is to generalize this. What about if our rational agent deals with a contextual probabilistic model? What if we have context as in quantum complementarity? Well, what you find is that the most rational choice is use quantum states as probabilistic measures. This is discussed here. But what about information theories? Well, something similar happens. The natural measures of information for quantum mechanics is von Neumann entropy. And for more general theories, you can define generalized information measures. So this implies that we have an information theory here, a different information theory here, a different information in more general theories. So let's jump this. So what are random variables here? Well, a random variable is classically a measurable function from an outcome set to the real numbers and satisfies these axioms. In the quantum case, the notion of random variable is replaced by the notion of projective value measure. Each self-adjoint operator in a Hilbert space can be put in one-to-one correspondence to a self-adjoint operation. So it is essentially the same. So, but the similarity is complete. But now you wonder, what are classical probabilities? Well, they are not gone. They are here again, because you may have a very complex abstract probabilistic model, or a logic which is not classical here. You have the 0-1 interval, but an observable will be a measure from a Borel algebra of measurable subsets to the lattice. And then this diagram commutes somehow, and these things here are classical probabilities. So classical probabilities are not gone. Each time you have a context, you will define a classical probabilistic model. But then, what about ontology? What can we do if we want to go beyond the subjective approach and say something about the nature of the models involved? Because the subjective approach is too poor. It is valid for all probabilistic models. But the problem is complicated. Because in the quantum case, the Cohen-Specker shows that it is not possible to establish a global valuation, Boolean valuation, to the elements of the lattice of projecting operators. And in this paper here by Andreas Doring, it is shown that the same holds for arbitrary von Neumann algebra. So in general, you cannot expect, due to the existence of these results, an interpretation based on bundles of actual properties for generalized probabilistic models. This is threatened. An approach for dealing with bundles of possible properties was developed in this paper and a series of papers by Olympia and other authors. So maybe an approach in this sense, which is related to the model Hamiltonian interpretation, could be very useful to interpret these models. The conclusion. We have studied the connection between the event structures associated to general non-Kolmogorovian models and measures representing states. We reviewed an approach in which states are regarded as functions measuring the degree of belief of a rational agent, assuming that possibly contextual phenomena is accepted as a starting point. In order to provide an ontological interpretation, we have also discussed the conditions under which these event structures can be related to properties of a system and inquired on the ontological aspects of such an association. But warning, the ontologies may be very different, because the fact that you can apply non-commutative probabilistic models to the study of cognitive sciences or language doesn't mean that you will find quantum phenomena there. So a lot of care must be taken here. Or non-locality. No, it only means something in physics. So due to the existence of generalized versions of the Cohen-Specker theorem, we find that for many of these models, the description of systems as bundles of actual properties will be problematic. The modal Hamiltonian approach could offer a nice alternative for physical models. Of course, there's always the easy way out, right? You can always go to hidden variables, and you can postulate something like Bohmian interpretation for generalized probabilistic models. It's not a problem. But in physical theories, at least, you will deal with the fact that these hidden variables should be contextual or highly non-local, as is the case in Bohmian quantum mechanics. Well, thanks for all. These are some papers in which you can find more information about this discussion.
Okay. We have 10 minutes left for questions, comments.
I don't know very much about this, but I know Turing has this quantum topos approach, and that involves non-classical logic. So do you have a comment about what the options are if we move to non-classical logic?
Well, I won't say that if you use, for example, this subjective approach, you will have a depart from classical logic. The whole thing is classical. It's very simple. You go to an event algebra, and you want to bet. Suppose that you go to a casino. If the casino is quantum, is classical, well, you can use classical probabilities. If the games are made up of quantum theory, maybe a most rational choice is to use quantum mechanics to model this. And this is what you do in the lab, and it gives you a lot of success. The thing is that when you try to put there's no departure of classical logic here. But the thing is that when you put here a structure, I'm using orthomodular lattices because they appear in many concrete physical models of interest. But you could use something much more general. Of course, this approach could be extended to more general structures and principles. If you want to work, you need to fix something, but you can imagine. The approach based on topos, for me, is very interesting, but it has some problems, at least from my point of view. They want to depart from, they don't like quantum logic, because they say, well, it's not Boolean, I don't like no rule. Well, but they replace the approach with an intuitionist logic. So I don't think what is the gain here. But I think that it is a very interesting approach. But at least, and of course, the approaches that want to departure classical logic are problematic. You know the story about Hilary Putnam. And, I mean, if you want to say that this is a non-classical logic, you need to specify what do you mean about this. Because logicians don't like to call this a quantum logic.
The reason I mentioned it is because you mentioned that wanting to have a Cauchy-Specker, your approach to Cauchy-Specker, and it feels like it makes sense. And the thing that struck me about the topos approach is it gives a very intuitive and very nice, quick proof of Cauchy-Specker. Like once you set up their framework, Cauchy-Specker kind of drops out. So that's
Yes, I think that it's a very interesting approach. But I don't know what these people say from the ontological point of view, but if you use this new logic of the topos approach, the logic is not classical either, or it seems to be not classical. I don't know what they say about this.
Yeah, no, I like your talk. I mean, I did my master thesis on conditional probability on von Neumann algebra. So
the problematic
so
subject.
that was a long time ago. But I wanted to just simply make a comment. I mean, you didn't say something that I object to. So I wanted just to say that when you say contest, as a physicist, I translate that into experiment. And you don't need to, and so contextuality in a sense is not such a great notion. It simply says that the result of an experiment depends on the experiment. And you don't need to go to Bohmian mechanics to have this relation between generalized probability scheme and Boolean scheme. Even on the level of Landau-Lifshitz, like I was mentioning yesterday, you have that a natural association between random variables and operators. No, that's what I was very briefly sketching yesterday. So in a sense, a theory like Bohm then can explain even more how you can reduce a generalized probability space to a classical probability space. Just pay attention to what Bohr told us, that namely that there are no pre-existing properties that are revealed by an experiment. The result of an experiment is due to the interaction of a system and an apparatus. This is true in standard Copenhagen and it's true in Bohm. But, sorry. And so, except positions. All the rest are not pre-existing. Yeah, sure. And the fact that a position is pre-existing can be just a non-relativistic effect. In relativity, well, people say Bohm mechanics cannot be done there because there is no position operator. It's just the basic beable does not need to be associated to eigenvalues on operator. So in the relativistic framework, you can have an X, a position, which is not associated to an operator, and nevertheless is reproducing, the dynamics is reproducing the result of quantum measurements. And that's all I wanted to comment. I mean, that there is this...
Can I ask? Yes, well, I agree partly in what you said in general, and of course I say it again. This thing here needs not to be fixed. It's very general. I mean, the family of orthomodular lattices is very general. And you could also say similar things for orthocomplemented posets. So I agree with what you say about observables. I do not agree that much with what you said about contextuality. I think that quantum contextuality is a very peculiar thing. Now there are a lot of research trying to characterize quantum correlations and quantum probabilities. I don't know if you know the work about Adam Cabello and others. I mean, you should know about this. So the fact that we have, of course, in the Bohrian approach, and this is completely sympathetic to this approach, we are taking as a primitive, in the subjective approach, you can take as a primitive thing that there will be context. And you cannot reduce the whole thing to a single context. If you want to give a complete description, you need complementarity. So you need a kind of non-Boolean algebra in general. The algebra of events needs to be non-Boolean because in one context you have a Boolean algebra, classical probabilities. In another, the same. That's it. But the pasting of the whole thing, and there is a pasting, is non-Boolean.
Sure.
So,
completely means experiments.
Completely, yes, yes.
It means
Let me mention something.
The result of experiment depends on the experiment which you do because the operators are not describing pre-existing properties apart from position.
No. If you take an orthomodular lattice, you can show that it can be expressed as a decomposition of maximal Boolean subalgebras. Yeah. Each complete quantum measurement defines a maximum Boolean subalgebra. Right. So there's no tension there. But my point is that when you want to compare contextuality that appears in cognitive science, blah, 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 and you want to compare contextuality on quantum mechanics, contextuality in quantum mechanics is a very definite thing. It's very different from other kinds of contextuality. There's something going on, which otherwise this conference was
not different. Otherwise, I agree with
it was really context. Contexts are describing Kolmogorovian probability. You can a conditional probability. You have, but this is not the same. So,
any further question?
I'm sorry to deflate the level of the conversation and betray my deep ignorance. But, right, so you go to some quantum information talks and you hear a lot about Bayesian probability and the quantum Bayesian interpretation, and I'm totally ignorant. This, on my surface, right, when I look at this, I see the frequentist approach. Does this also, I just don't know anything about Kolmogorov probability theory. Can Bayesianism be fit into this framework?
Very nice question, thanks. I didn't talk that, I just skipped the thing, but the subjective approach that I'm mentioning here can be considered as Bayesian. It's another variant of quantum Bayesianism. Why? This guy, R.T. Cox, has this kind of philosophy. He says, well, if you're a rational agent, you're here trying to bet, make some bets. There are many approaches to bet. You have definite, you have a plethora of. But R.T. Cox says, if you have a Boolean algebra, if you throw a dice, you will find the Boolean algebra. So he justifies you doing some mathematics that the most rational choice is Kolmogorov probability theory. So the question is, suppose that you cannot reduce the whole thing to a Boolean algebra. That is the question that we posed in this paper. Suppose that you deal with contextual phenomena, as in Bohrian quantum mechanics. You know in advance that in order to describe your system, you need a Boolean algebra here, but another Boolean algebra, and another one to make the complete tomography of the quantum states. What is the most rational choice? Well, we show that it is to use quantum states. In this sense, quantum states are the non-commutative version, or the non-Kolmogorovian version, or the non-Boolean version of the Cox approach. So it's a natural explanation of why you are using this quantum thing, which is, if you look at this from this point of view, it's not so strange. Of course, I'm not claiming that the complex things go away, but it's a nice approach. But you are not saying nothing, almost nothing about ontology here. So I was just posing the things on the table. But I don't know why, but some people think that Cox is not that Bayesian as it seems, but I don't know.
Okay, thank you very much.